Dear students, welcome to 9th online class of Control System Engineering. In this class, we will start chapter 3, which is Modeling in the Time Domain. In first lecture of Control System Engineering, we have discussed the course flow, which starts from mathematical modeling of a physical system. Then from mathematical model or ordinary differential equation, we will find out transfer function or state space model. Now we will study how to find state space model of a system. Dear students, as discussed in chapter 2, in classical control, we analyze a system in frequency domain or Laplace domain, where in modern control, we study or analyze a system in time domain. Dear students, by the end of chapter 3, which is modeling in time domain, you will have skill to represent mathematical model or dynamics of any linear time invariant system in the form of state space representation. By the end of this chapter, we will also study how to represent electrical and mechanical system in state space form. Dear students, now coming to the contents of this lecture, we will start from the definition of a state space. What is a state variable, a state vector, state equation, and output equation. Then we will study transfer function versus state space. And finally, we will study how to make a state space representation for any given physical systems. In the given examples, we will study how to make state space representation for electrical network and translational mechanical system. Dear students, state space is a mathematical representation of any physical system. This mathematical representation includes set of input, output, and state variables. So basically, for a state space representation, we have two equations. First equation is known as state equation, where second equation is known as output equation. Dear students, as you are familiar with input and output, now we will study state variable. A state variable is a set of parameters or variables which provide sufficient information about the system at any instant of time, or any variable that responds to an input or initial condition in a system. For example, consider we have a translational mechanical system. In this, displacement of a body is a state variable. In an electrical network, charge flowing through the components is a state variable, and the angular velocity in rotational body is a state variable. These variables provide information about the system at any instant of the time. State variables are identified from the system under consideration, and these variables should be dynamic in the system. State vector. A vector who is formed by state variables is known as state vector. Students, now we will study state equation and output equation. These both equations combinedly form state space representation of a system. First is state equation. A set of simultaneous first order differential equation of state variables is known as a state equation. As studied, a state variable is a set of parameters which provide sufficient information about the system, and these variables must be dynamic in the system. So when these variables are represented in first order differential form, this is known as state equation. Next is output equation, an algebraic equation that expresses output variables of a system as linear combination of state variables and inputs. In these equations, x is a state vector, x dot is derivative of state vector with respect to time, y is output vector, u is input or control vector, a is system matrix, b is input matrix, c is output matrix, and d is feed forward matrix. And mostly feed forward matrix is 0. If you look at the figure, it represents state space representation of two states. One is VR and second is VC. The curve represents trajectory of a state vector. The first state vector we have is x of t. As time increases or system start its movement, its states also get changes, and these changes are represented in the form of curve. And x4 represents state vector at time instant t equal to 4 seconds. Dear students, now we will discuss some basic differences between transfer function and state space. Transfer function is relation between input and output, or it is a ratio of input divided by output. It helps us to analyze a system in frequency domain, where state space involves input, output, and state variables, and it is represented by state equation and output equation. In this, we analyze a system in time domain. Dear students, with the help of state space, we can represent dynamics of a physical system in time domain. For this representation, some steps are followed as discussed below. For state space representation, first of all, we will identify all the dynamic variables which give sufficient information about the system at any instant of time. And these variables will be termed as state variables. In second step, we will represent this state variable in the form of first order differential or difference equation, known as state equation. Let we have system of nth order. For this, n state variables of the system will be represented in n first order simultaneous differential equation. Now for given initial conditions and input to the system, we can solve the simultaneous differential equation for the state variables and can find out behavior of a system for any time instant greater or equal to initial or start time, which is t0. After solving these state equations, we can obtain output of the system as combination of input and state variables. And these equations are known as output equation. The set of combination of state equations and output equation form a state space representation for any physical system. Dear students, as an example, A linear time invariant second order system is represented in state space model where x1 and x2 are its state variable, a single input v of t. In first equation, x1 derivative is equal to linear combination of states and input. In second equation, first derivative of x2 is equal to linear combination of states and input, where output equation is linear combination of states and input. Now with the help of example, we will study how to form a state space representation for any system. In the given example, we have to make a state space model for an RLC network. Dear students, first step in analysis of any system is to find out ordinary differential equation defining dynamics of that system. For this RLC network, first of all we will write KVL equation, which is first equation of this slide. Now we will identify state variables for this RLC network. As we know, we can replace current by charge using the relation current is equal to rate of change of charge. And we get second order differential equation for the system. Now for this system, we have two state variables. First one is charge and second one is current. Now after identifying state variables, we will write these state variables in the form of first order differential equation. Dear students, now we will represent state variables of RLC network as first order derivatives for state equations. Our first state variable is charge flowing through the circuit, and second state variable is current flowing through the circuit. We know that current flowing through the circuit is equal to rate of change of charge, or we can say that rate of change of charge is equal to the current. Through this we obtain our first differential equation. Now for first order differential equation of current, we will use KVL equation of the circuit. This equation, integral of current will be replaced by charge, then terms involving derivative of current will be on one side of equation, and all other terms will be shifted to other side of the equation. And with this we will get second equation for state model. Now both the equation involving terms first order derivative of state variable represent state space model for the system. Students, we are observing voltage drop across inductor as a output of the system, and its relation can be obtained through KVL. State space model of linear time invariant system can also be represented in matrix form, which is x dot equals ax plus bu, where A is system matrix and B is input matrix. These matrices contain coefficients of state variables and input from first order set of differential equations. Here x is state vector, which includes charge and current, and x dot represents rate of change of state variables with respect to time, and U is input of the system. Now output of the system can also be represented in matrix form, where Y equals Cx plus Du, where C is output matrix and D is feed forward matrix. Dear students, here in another example of RLC network, we have to make state space representation where output is the current through the resistor. In the solution of this example, at first we will label all the branch currents. This includes current through the inductor, which is represented by IL, current through resistor, which is represented by IR, and current through capacitor, which is represented by IC, as shown in figure. Now we have to find out state variables for this system. In this system, current through the inductor and voltage across capacitor are our state variables. And this is obtained by writing derivative equation for all energy storage elements. Now we know that current through capacitor is equal to capacitance of capacitor multiplied by rate of change of voltage. Voltage across inductor is equal to inductance of inductor multiplied by rate of change of current flowing through it. Now both these equations represent first order derivative of our state variables, but in state equations, first order derivative of state variable is equal to linear combination of states and input. Now to complete this state model, we will use Kirchhoff voltage law, Kirchhoff current law. Dear students, now we will apply KCL or KVL to complete our state equations model. Now if we apply Kirchhoff's current law at node 1, we obtain current through the inductor is equal to current through resistor plus current through capacitor. And from this, current through capacitor will be equal to minus current of resistor plus current through the inductor, where current through resistor is equal voltage across resistor divided by resistance of resistor. As resistor and capacitor are in parallel, so voltage across capacitor is equal to voltage across resistor. Now we will apply KVL at outer loop, from which source voltage will be equal to voltage drop across inductor and voltage drop across capacitor. And from this, voltage drop across inductor will be equal to minus voltage across capacitor and source voltage, which is V of t. Now substituting these values in derivative equation for all energy storage elements and making rearrangements, we will obtain our desired state equation model for the system. Dear students, now with rearrangement, we will obtain our state equation model for the system. Now for output, we know that current through resistor is output of the system, and the current IR is equal to voltage across resistor, which is also equal to VC divided by resistance of resistor. Now the equation 3.27a, 3.27b and 3.28 completes the state space representation for this RLC network. As this RLC network is made up of linear components, so this state space model can also be represented in matrix form. Equation 3.29a represent state equation model in matrix form, where equation 3.29b represent output equation in matrix form. Dear students, now with the help of example, we will find state space model for a translational mechanical system. Dear students, in this example, we have two masses M1 and M2 lying on a frictionless surface. M1 is connected with viscous damper D, and M1 and M2 both are connected through a spring with coefficient K. Motion of M1 is represented by x1, where motion of M2 is represented by x2. Finally applied force act on mass M2. This system has degree of freedom equals 2. So we will obtain our desired equations of motion following the rules or steps related to translational mechanical system discussed in chapter 2. And both equations are given here. Dear students, now for state space representation of translational mechanical system, we have to identify the state variables. For these state variables, we will analyze the system. As the system consists of two masses, M1 and M2, and both masses are moving in the given direction of motion. M1 is moving in the direction of x1, where M2 is moving in the direction of x2. Now in general, whenever we apply a force on any object, and with this movement, this object covers some displacement. During the time at which it is moving, it has some velocity and also it has some acceleration. So students, these three variables are associated with motion of an object. Now if we look at the relation between these variables, we know that rate of change of displacement is velocity, rate of change of velocity is acceleration, and as a rule we have to choose minimum number of variables for the state space model of a system. So here x1 is representing displacement covered by mass 1, and its derivative, which is dx1 over dt, will represent velocity or v1. Now rate of change of velocity will be acceleration, which is equal to double derivative of displacement x1. So x1 and v1 will be two state variables for mass m1, which will be representing displacement, velocity and acceleration. Now for m2, its displacement will be represented by x2, and its derivative, which is dx2 over dt, will represent velocity. For velocity, we will also use variable v2. So v2 equals rate of change of x2. Now acceleration of mass 2 will be rate of change of velocity or double derivative of x2. So x2 and v2 will be state variables for mass 2, which will be representing its displacement, velocity and acceleration. Dear students, equation 3.44 and 3.45 defines equations of motion for this system. Now we will substitute state variables for both masses m1 and m2 and their differential relation into equations of motion 3.44 and 3.45, and with rearrangements we will get our desired state equations, which are from 3.46a to 3.46d. As this system is linear, so we can also represent its state space form in vector matrix form, given in equation 3.47. Now if any of you have any questions, please ask.